Hey everybody, it's Brandon from STEM Tutor Club, and today I want to talk about one of the first things that you come across in an Algebra 1 class, and that is exponent properties. Specifically, today I want to focus on this one here, the first one, which is usually called either the product rule or the product of powers rule. And basically, with all of these properties in a class, you're normally just given them to remember, but that's sort of confusing and they're difficult to remember. So the thing I want to talk about today is why each one of them makes sense, and I found that that makes it easier to remember. So here I have an example with actual numbers written out as opposed to the format that you usually see it with just the letters, where the letters are basically placeholders for other numbers. So A is usually the base, and then you could have M and N as the exponents, or sometimes X and Y, as we had above. But here you can see what it looks like with actual numbers. So if we assume that A is equal to 2, well then any place where we have A in this equation, we should have 2 with our actual numbers. And then so that would be like the left side of the equation, and this would be the right side of the equation where we have just one A. And then M is the first exponent, which is 3 here, and then N is the second exponent, which is 4 here. You can see that. And now, basically what I want to do is just test out, does this work? So the first thing that we can do here is calculate 2 to the third power, and you can follow along with a calculator if you want to verify these, but 2 to the third power is equal to 8, and then 2 to the fourth power is equal to 16. And then if we kind of come over here and we do 16 times 8, if you want to do it by hand, then 8 times 6 is 48. Carry the 4, 8, and then 12. So it should be 128. And then over here, the property says that whatever these powers are, 3 and 4 in this case, then we should be able to add those properties together, which is how we get 2 to the seventh power. And then you could verify this in a calculator if you want. So 2 to the first power would be 2, to the second power would be 4. Then basically every time you increase the power, you double. So if we wanted to create a table over here, so this would be like the exponent. So this would be like n, and this would be 2 to the n. So if we created a table, it'd be 1, 2, 3, 4, 5, 6, 7, because we want to go all the way up to 7. So if we start off with 1, that would be like 2 to the first power, which is just 2. 2 to the second power, 2 squared would be 4, 8, 16, 32, 64, and then 64 times 2 would be 128. So you see that we really do get 128 equals 128 when we're basically just testing out if this works. So that's just one example. This actually works for any numbers, no matter what A you pick, no matter what M you pick, and no matter what N you pick. You can pick any three numbers. Some exponent properties you cannot pick 0 for A because you would have division by 0, but we don't have that problem here. You can pick any numbers, and this is guaranteed to work. But this is just an example of how it works with one of them, that we can prove it. So going on to the second example here, which is actually simpler than the first one, we're going to set M equal to 3, the first exponent, the second exponent N equal to 2, and then we're going to set our base A equal to 1. And then here, it's even more obvious why this one is true. Because 1 cubed, that'd be like 1 times 1 times 1, if you want to think of it like that, which is just 1. And then 1 squared is 1. 1 raised to any power is equal to 1. So you're going to end up with 1 times 1 on the left, which just simplifies to 1. And then on the right here, according to this formula, we can just add the two exponents, so 3 plus 2 here to get 5, and we'll just be left with 1 to the fifth power, which is also equal to 1. So here, this checks out as well. You can see that this is also valid. And then here's one last example with the numbers that we were talking about before. So here our base is going to be 3. So A is 3 here. M, our first exponent is 2. And N, our second exponent, is equal to 3. So we can actually test out if this works. So 3 squared here, that's going to be equal to 9. 3 cubed, that would be 3 times 3 times 3, which is 27. And then over here, apparently that's supposed to equal 3 to the 2 plus third power, which is 3 to the fifth power. So we need to check if this is really true. So if we come down here, so we'll actually calculate 27 times 9 the hard way. So 7 times 9, that should equal 63. And then 9 times 2, that should be 18. Carry the 6, so that should be 224 to give us 243. And then over here, basically if we kind of do a similar thing to what we did last time, whereas if we start with our n on the left, and then we'll have this time 3 to the nth power on the right. So we'll do 1, 2, 3, 4, 5. And then basically every time we're gonna start off at 3 to the first power, which is 3, and then every time we're just gonna multiply by 3 for what we had in the last one. So 3 times 3 would be 9. In other words, 3 squared is equal to 9. And then here, 3 cubed would be 27. And then if we multiply that by 3, what will we have? So if we do 27 times 3 over here, that'll be 21, and then that'll be 6, carry the 2, so that should be 81. And then to find the fifth power, which is what we're actually looking for, we can just take 81 and multiply by 3. So now if we do 81 times 3 over here, so 3 times 1 is 3, and then 3 times 8 is 24. So we get 243 again. And by the way, this is just proving it by hand. You could have also proved it just by plugging it into a calculator. You can literally plug in 9 times 27 into your calculator, see that you get 243, and you can also plug in 3 to the fifth power to verify that you also get 243. So that's three examples with relatively simple numbers to work with for why this works. But with this exponent property, we can also talk a little bit more abstractly. So in previous examples, we basically chose numbers for a, m, and n. Here, we're going to choose numbers for m and n, the exponents, but we're going to actually leave the base as an unknown. So in other words, we're going to set it equal to the variable x, which represents that we don't actually know what the base is. And if you ever see something written like this, basically you can simplify it using this exponent property, and instead of expressing it as x to the third power times x to the fourth power, you can instead express it as x to the seventh power. And you can see that that's simpler, that's less writing. So this is like a simplified version of the same expression. They're equal to the same thing if this exponent property is true, which it always is. But this formula right here, this is what I want to explain. I want to explain why this makes sense logically, and that's what we're going to do now. So here, before we get into the general case where the base is an unknown that we set to x, we're going to work with actual numbers first to understand why this makes sense. And actually, this property here is pretty straightforward if you just think of the definition of exponents. So what does an exponent mean? What does 2 to the third power mean? Well, basically it means we take the base, which is 2, and we multiply it by itself 3 times. That's all the exponent means. So this 2 to the third, we can represent that as 2 times 2 times 2. That's all 2 to the third is. And then we have this multiplication sign here, and then we have 2 to the fourth. So what is 2 to the fourth? Again, same argument, except that we have an exponent of 4 instead of 3, which means we should multiply 2 by itself 4 times. So in other words, we should have 4 2's multiplied together instead of 3 2's. So if we work that out, 2 times 2 times 2 times 2. Now you could plug this into a calculator if you want, but you don't actually need to do that, because what we could do is we could do some properties which are called the commutative and associative properties of multiplication. You don't have to really get hung up on that, but basically what they mean is that whenever we're multiplying a bunch of things together, we can put parentheses around whatever we want or get rid of any parentheses that we want. And we can also order things around. So here, all I'm going to do is just drop the parentheses. That's really comes from the associative property of multiplication, but it's sort of obvious, so you don't really need to think about it that strictly. But if you break it down, we're going to have 2 times 2 times 2 times, and then without the parentheses, 2 times 2 times 2 times 2. 2 times 2 times 2 times 2. And you can see that this is actually equal to, what is this? This is 2 multiplied by itself 1, 2, 3, 4, 5, 6, 7 times. By definition, that is 2 raised to the 7th power, because that's what the exponent means. The 7th power means that we need to multiply 2 by itself 7 times, which we do here. So when you write it out like this and actually expand the exponent into the multiplication that it represents, the property is almost obvious. And that's what I'm hoping to convey here. And finally, we're going to take what we just discussed and apply it to the more general case where we have x to the third and then x to the fourth. So if I break that apart, we don't know what x is, but we can expand this as x times x times x. That's by definition x cubed. And then we have the multiplication sign, and then same thing, x to the fourth will be x times x times x times x. X times itself 4 times. And then we can basically drop the parentheses and group these. So we'll have 1, 2, 3, 4, 5, 6, 7, which is x to the 7th, no matter what x is. You can see that. And now I want to show you the most general case where we have an unknown x in the base, and we also have unknown exponents. So here, the way this is typically represented is we have x times x times x, and we don't know how many times we're multiplying it by itself, but we can sort of represent this as saying that we're doing this m times. So there's basically m x's multiplied together. And then we have the multiplication sign outside the parentheses, and then we can sort of do the same thing here. So x times x multiplied by itself n times. And if you count these up, well, we have m x's right here, and then we have n x's after that. So clearly, if we add those together, we should have m plus n x's, which is by definition x raised to the power m plus n. So again, this is a proof that you would typically see in your book, but we don't actually know what m and n are, but we can sort of reason about what it must look like using the similar logic that we used with actual numbers, and we're applying it to this case where we don't actually know the numbers, but it follows the same pattern. And so that's the most general way to prove this basic formula that we have here, and this comes up quite a bit as well when you get into polynomials and more equations like that in your algebra class. So in this video, we went over this first exponent property here, and hopefully this makes sense. Be sure to stick around as we go over all these other exponent rules to understand why they make sense too.